All right, in Chapter 2, we were able to solve a few first-order differential equations by recognizing them as separable, linear, exact, or having homogeneous coefficients. Even though the solutions we obtained were in the form of one parameter family, this family, with one exception, did not represent the general solution of the differential equation. Recall that a general solution is a family of solutions defined on some interval that contains all solutions of the differential equation that are defined on. Only in the case of the linear first-order differential were we able to obtain general solutions by paying close attention to a certain continuity conditions imposed on the coefficients of the equation. Because our primary goal in this chapter is to find general solutions of higher-order differential equations, we need to first examine some basic theory of linear equations. Okay, so in short summary, we looked at a bunch of special cases. So we didn't know why they were special cases because we didn't tell you why. Now we're going to generalize this to pretty much attack anything other than, or not anything, to look at differential equations that are higher than a linear order. Okay, so let's start with the basic understanding of an initial value problem. So for a linear differential equation, we refer to them as an nth order initial value problem. And you can see just the general format that allows us to look at more than just the linear form. And so our first task is going to be just to verify this particular solution. So let me kind of scroll up here. All right, so let's first figure out what the second derivative of y is. So y prime is 6e to the 2x minus 2e to the negative 2x minus 3. And double prime would be 12e to the 2x plus 4e to the negative 2x. That's it. Okay, so I want to take that double expression there. So 12e to the 2x plus 4e to the negative 2x, sorry, should be an x there, minus 4 times y. And I need to solve for y. I don't have, oh, no, never mind. So 3e to the 2x plus e to the negative 2x minus 3x. And that's going to equal 12x. Okay. So let's see. If we simplify this out, we get 12e to the 2x minus 12e to the 2x plus 4 minus 4, and then that gives me 12x equals 12x. Okay, so that in fact checks out. Hooray. Another type of problem consists of solving a linear differential equation of order 2 or greater in which dependent variable y and its derivatives are specified at different points. A problem such as the general pattern given to you is called a boundary value problem. The prescribed values are called boundary conditions. A solution of the foregoing problem is a function satisfying the differential equations on some interval containing a and b and whose graph passes through the given sets of points. Okay, so graphically that's kind of what we're talking about, is that the solutions of certain differential equations that satisfy certain points, there might be multiple equations that satisfy those given sets of points between a different set of intervals. Okay, so let's have a sort of an exploration about this idea of boundary conditions. So I've got a differential equation, x double plus 16x equals 0, and I've got a general solution, x equals c1 cosine 4t plus c2 sine 4t. And let's put some boundaries. So let's say we're going to say x of 0 equals 0, so it goes to the origin. And then let's say I know for a fact that at pi halves it equals 0, or maybe at pi over 8 it equals 0, or pi halves equals 1. What impact does that second term, or essentially the boundaries, what impact would the boundaries have on potential solutions? So let's just evaluate the solution with these two boundary conditions and see what do we notice, right? So x of 0 equals 0 says 0 would equal c1 cosine of 0 plus c2 sine of 0, right? And so that would imply that c1 itself has to be 0 and x is c2 sine of 4t, just with that first condition, right? So let's look at the second boundary point. The second boundary point, when I evaluate that, so I get 0 equals c2 sine of 4 times pi halves. So that's sine of 2 pi. Right? Sine of 2 pi is 0. Or c2 times 0 there. In essence, we don't, doesn't really matter what the value of c2 is. Any value of c2 would satisfy this set of boundary conditions. So we have an infinite number of solutions that'll work here. So there's an infinitely many solutions because of the two boundary conditions that we were given. So any value of c2 would completely work. Okay. What about if it was pi eighths instead of pi halves? Okay, so we know that first condition simply tells us that x is defined by c2 sine of 4t. So c1 itself is going to be 0 because of that first condition. All right, and if I evaluate that, so I get c2 sine of 4 times pi over 8. So 0 equals c2 sine of pi halves. And so that says that c2 times 1 has to equal 0, and we're locked in that c2 has to be 0. Okay, so that says then that there is a single solution, one solution, and it happens to be when c1 is 0 and c2 is 0. It's the only solution that satisfies that. Okay, so what about the third case? Okay, so that initial boundary condition still tells us that x is equal to c2 sine of 4t, and then 1 equals c2 sine of 4 times pi over 2. And so that's c2 times sine of 2 pi, which is 0, so c2 times 0. Okay, so now we got a problem because there is no number c2 that would ever make that statement true. So this is a situation where there's no solution. So no combination of c1, c2 would ever make that true.